All right, guys, welcome to this page of the notes, and I'm really excited about this. I mentioned before, actually, when I first started teaching, my first couple of years of teaching, I actually taught general chemistry and AP chemistry. I love chemistry, and even more, I really like it when we're able to take what we're learning in Algebra 2 and apply it to something you've seen in another class, and hopefully that helps you understand both what's going on in Algebra 2 and what's going on in that other class a little bit more deeply, because you're able to make those connections across disciplines, across different subjects. So in this case, we're going to be taking a look at chemistry, and one of the things you do in chemistry, there's an entire chapter dedicated to gases. And in particular, when it comes to gases, the way that a couple of variables, like the volume of a gas, the pressure of a gas, the temperature of a gas, and the moles of a gas are all related to each other. And it turns out that the way those guys are related to each other is what we call the gas laws. But the gas laws in chemistry are nothing more than variation functions like what we just looked at. So let me put right here, the gas laws are variation functions like we just looked at. Let me show you. Let me show you how this works. In particular, one of the gas laws you should recognize if you've taken chemistry is Boyle's law. And here's what Boyle's law says. It states that when a sample of gas is kept at a constant temperature, all right, so the temperature is the same, we don't let the temperature fluctuate. As long as the temperature is held constant, the volume varies inversely. Check that out. That should now jump off the page at you. The volume varies inversely with the pressure exerted on it. We have just looked at inverse variation relationships. You should at this point be able to write a function for that, and we will. So here's what I want you to do. I want you to write an equation for Boyle's law that expresses the variation, right? The variation in the volume, which is given by a capital V, as a function of the pressure, which is given as a capital P. Now, I know I've got it written there for you, but here's what you would do, right? You're sitting in chemistry class, you go, oh, look at that. The volume varies inversely with the pressure. Well, I know inverse variation is volume varies inversely. That means it is K over varies inversely as the pressure. So the P goes in the bottom. But K is a constant. K is the constant of variation. So we'll solve for K, which means that K is equal to volume times pressure. Now, the real important thing here is this. What we showed you how to do in this section, Chapter 8, Section 5, is look at two different conditions, an initial set of conditions and a final set of conditions. And that's exactly what we're going to do. I'm going to give you a sample of a gas. I'll tell you the volume and the pressure, and then I'll change one of them. Either I'll increase the volume and ask you what happens to the pressure, or I'll increase or decrease the pressure and ask you what happens to the volume. But you already know it's an inverse relationship. You know that they have to go in opposite directions. But the point is this. You'll have an initial set and a final set of conditions. So you take what you now know about inverse relationships. The volume varies inversely with pressure. V is equal to K over P, which means K is equal to VP. Initial and final set means that I would have V1 times P1 is equal to V2 times P2, right? Initial set of conditions, final set of conditions, and you can solve for any one of those variables. So let's go ahead and apply Boyle's law here in an example problem. What I've told you is I'm asking you to find the volume of a gas at a pressure of 2 atm. Again, atm just simply stands for atmospheres. Normal atmospheric pressure is 1 atm. Again, that depends on your elevation though. So 1 atm at sea level, we'll just assume we're at sea level and we're applying a pressure of 2 atm. So 2 times the normal atmospheric pressure. If the initial volume was 3 liters, the volume of gas is 3 liters. Of course, volume is measured in liters, the standard metric units. I want to know, I apologize. I want you to find the volume of gas at 2 atm if the initial volume was 3 liters, the pressure was 1 atm. So volume will, right, what we want to do is we're changing the pressure. I'm going from 1 atm to 2 atm, so I'm increasing the pressure. What happens to the volume? Well, again, think about it for a second. You already know, just based on what we talked about inverse relationships. I had a pressure of 1 atm. I increased it to 2 atm. That means the pressure has gone up. It's an inverse relationship. So what has to happen to the volume? It's got to go down. It has to. So I was told my volume was 3 liters. When I get my answer, it had better be less than 3 liters or you done goofed. And you have to go back and figure out where you made your mistake. So here we go. V1, V1, P1 is equal to V2 times P2, and we plug and chug. My volume was 3 liters at 1 atm. That's my initial set of conditions. My final set of conditions, I increased the pressure to 2 atm. I want to know what is the volume. So V2, 2 atm. Solve for V2, I would then have 3 liters times 1 atm over 2 atm, right? Divide the 2 atm to the other side. Units of atms cancels with atms. I'm left with units of liters, which is perfect because I know it's a volume, and I wind up with 3 halves or 1.5 liters. 3 halves liters, which is 1.5 liters. And exactly what we just said happened. I know that the pressure, right, the pressure went up. I went from 1 atm to 2 atms. If I increase the pressure and it's an inverse relationship, the volume's got to go down. It has to. It's an inverse relationship. That's exactly what happened. I went from 3 liters down to 1.5 liters. Guys, again, I love it. I love it when we're able to take something we're learning in Algebra 2, because students ask me all the time, how will I ever use this? When does it apply? And it's great when we're able to see an application in another subject area of how the Algebra 2 we're learning applies in other subjects, in other disciplines. So head on over to the next page of the notes. We'll take a look at a couple more gas laws and how they work, and I'll meet you guys there.